So today I'm going to talk about not a distance geometry problem, but it's a problem that arises in NMR spectroscopy. So we know that the distance geometry problem is a central problem in NMR spectroscopy, but there's a very important pre-processing step before you enter distance geometry. Before you enter the distance geometry problem in NMR spectroscopy, and I will talk about it in this talk. It's going to be a very applied talk, and I hope you enjoy it. All right. So yeah, this is joint work with Jose Ferreira. He's a student of Amit Singer, and I was also a student of Amit Singer 3 years ago. Yeah. All right. First, I'm going to talk about NMR spectroscopy in order to introduce the problem properly, and I'll talk about how NMR assignment problem arises in this application, and I'll survey some related work. Then I'll talk about some approaches that we have taken to solve it. First, we formulate it as a quadratic assignment problem. Then later, we also try approaches like formulating it as a shortest path problem, which works better. And I'll conclude. OK. Why do we care about NMR spectroscopy? So NMR spectroscopy is the only tool for structural determination when you have protein in solution. So that means you don't need to crystallize protein, unlike in X-ray crystallography. And we know that this is a very difficult experimental procedure. It also allows structure reconstruction at the atomic level. So this is unlike, for example, the currently very popular method, cryo-EM, which works for larger molecules. We can actually reconstruct small molecules like 10 kilodalton, 20 kilodalton at atomic level. However, on the other hand, the data quality quickly deteriorates with increasing protein size. When the protein size is larger, you start having a lot of missing measurements, making your problem ill-posed. And the computational pipeline is not fully automated at this point. All right, let me first talk about the computational pipeline so that you know where the assignment problem arises. We have some protein of unknown structure in the solution. This gives rise to free induction decay with various frequencies. So these are essentially some exponentially decaying sine waves with different frequencies. Then you take the Fourier transform. You start seeing this type of 1D spectra. Yes. And the next step is you do a peak picking. So essentially, you select out the peaks. OK? In the ideal world, you should have the same number of peaks as the same number of atoms in the protein. Now, once you saw this resonance peak, you want to label the.
May I ask you something?
Yes.
I've always tried to understand this thing, and I've been told many times, but I still don't understand.
Yes.
I apologize.
No.
The raw data comes from vibration. What is vibrating? The protein in the solution.
So essentially, you give it some excitation,
Okay.
and then with electromagnetic pulse, and it will start doing precession. The spins will start doing precession. Then you see this type of a sinusoidal wave.
There is a pulse, and this is where it vibrates, and then it dies down.
Yes, it dies down. So it will do some precession, and then the sinusoidal oscillation is essentially the effect of a rotating magnet inside a coil, and it's picking up the signal of a rotating magnet.
Thank you very much.
And you have a lot of rotating magnets because each individual atom is actually a rotating magnet. Now you want to label each of these atoms with the resonance peaks that you're observing. However, you're just seeing a bag of resonance peak. Then you need to solve an assignment problem in order to assign these peaks to the atoms over here. OK?
So let me just sorry.
Yes.
But the data you're showing there are usually the one-dimensional traces.
It's a one-dimensional trace.
They're from a particular frequency which corresponds to a particular atom, and then it's watching the decay at another
Yes.
atom which is separated away by something.
That will be a 2D spectra.
Yeah, if you change the first atom.
Yeah.
You just do one atom and then see the decay at other atoms.
Right.
Each peak is the other atoms.
Yes.
Distance, yeah.
Yes, exactly. But if you are varying the excitation time of the first atom, that will give you a two-dimensional spectra because you have two times. One is the excitation time of the first atom. One is the decaying time of the second atom. You start seeing, yeah. Right. So, so once you label the atoms with the frequencies, you can start placing constraints between the atoms. And this is where the distance geometry comes in. Okay, once you start having geometrical constraints between, for example, these two orange atom over here, you can start solving for your structure. Okay. Now, okay, all right. Let me go into further details for this NMR assignment problem. Okay, so like I said, we have a list of picks from the experiments. So we have done pick picking, we have selected all these resonance picks. Now we want to start doing assignment. And the first type of information we have are basically some prior informations about. So for example, if you have a specific atom in a protein, you expect its resonance frequency to lie in a certain range. This is a type of prior information you have. However, a lot of times, actually most of the times, within the frequency range, you see multiple resonance peaks. That means you don't get a unique assignment from the resonance to the atom. Then you actually need more information, like what Phil says. You need some high-dimensional spectra in order to facilitate this assignment procedure. And I'll explain next in the next slide. Well, a peak can be, you can have a 1D spectra, you can also have 2D spectra and 3D spectra. The idea is the following. Okay, so for 1D spectra, you have seen this. You pick the peaks, and then you can plot them on the real line. This is 1D spectra. However, this is a graph for 2D spectra. And then after you perform peak picking, you start seeing a spectra like this. And I'll explain what this means. If you see an orange peak over here, that means there is some, this is the x-axis is the frequency for nitrogen, and the y-axis is the frequency of hydrogen. When you see a peak over here, that means there is a nitrogen with this specific frequency indicated by the x-axis, and some hydrogen with this specific frequency. These two pairs of atoms are interacting. So what it means is, yes? For this procedure, it's not that important. Okay. So what it means is the following. You have some resonance frequencies, okay? And based on this type of higher dimensional spectra, you build an interaction network of this resonance peak because you know two frequencies are interacting with each other. Once you build this interaction network, and you take your protein and you use chemistry to build an expected interaction network, and you perform a graph matching, this allows you to pass the frequencies from the spectra to the atoms in the protein. I hope this procedure is clear. Please ask me a question at this point if you are not sure if I didn't do a good job in explaining.
So these peaks that you're talking about here, the through space ones from the nosy interaction as well as through the backbone?
Yeah, these are, for this procedure, it's typically through the backbone because this is more reliable. Yeah, because the expected peaks usually will exist in the spectra, but the through space interaction nosy, even you're expecting it due to spin diffusion or whatever mechanism, you usually don't see it. A lot of time you don't see it. You have missing peaks. But the through bonds interaction, if you're expecting it, you see it most of the times. Yes. And you also have 3D spectra. For example, if you see a peak over here, that means you have some carbon and some nitrogen and some hydrogen of the specific frequencies indicated by the x-axis, y-axis, and z-axis. They are interacting. Okay. So based on this, you can build an interaction network of the resonance peaks, and you take your protein sequence, the amino acid sequence, and then you build an expected interaction network, and you perform a graph matching.
So I can see how to represent these two-dimensional interactions with a graph.
Yeah.
I can see more so it's harder for me to see how to represent the three-dimensional interactions with the graph unless you talk about hypergraph or unless you replace them with.
Yeah, it's like a hypergraph. So you can think about the interaction. I mean, if you think about like a more general, for example, graphical models, you can model this as a clique in the graphical model if you have three things interacting, and the variables are the atoms. Yeah. So right, you can.
Can you infer distances also from the three-dimensional models?
Usually, well, these interactions are not NOE measurements. So essentially, once you identify which pairs are interacting, you automatically know their distance because they're interacting through bonds, and you know the bond length from chemistry. You know the. Okay. Actually, I'll try to go slower, and I'll just finish half of the talk. Okay. So in order to perform this matching procedure, I need to tell you how these peaks are actually generated from protein sequence. Okay. All right. Let's look at this sequence of residuals. So protein is made of a sequence of residuals. They have repeated structure. So the first very classical spectra is coming from the interaction between the nitrogen and the hydrogen attached to the nitrogen. So these two, when they're interacting, you see a two-dimensional spectra of this form. So since each residue will have one pair of a nitrogen-hydrogen pair, so on this spectra, you're going to see the same number of peaks as the number of residues in the protein. Okay. So the next one is HNCACB three-dimensional spectra. So what this gives is the following. How is this generated is from the following. You have the hydrogen and nitrogen pair interacting with the carbons from the adjacent residue. Okay. Essentially, this carbon is interacting with this two, this pair of nitrogen-hydrogen, and this carbon is also interacting with this hydrogen-nitrogen. So this will give these two orange peak over here. Okay. So, and you see that these two orange peak will have the same Y frequency and the Z frequency. That's because these two carbons are interacting with exactly the same pair of nitrogen-hydrogen. Okay. So essentially, if you look at this, it should form a tubular shape. And similarly, you have a different spectra that will you have a nitrogen-hydrogen, the same nitrogen-hydrogen interacting with the adjacent carbons and the carbons on the same residue. So all in all, I'm saying each residue will give rise to a peak that looks like this in the 3D spectra. So if you look along the x direction, it will form this one-dimensional tube. Okay, that's because they are interacting with the same pair of nitrogen-hydrogen. Okay. Now, right. So essentially, this is a graphical summary of what I was trying to say. Each residue will contribute these peaks of 4 resonance. This set of 4 resonance. Now, once you perform the peak picking, you start forming these strips of set of 4 resonance, which is associated with each residue. Then if you sort them correctly, you're going to see this pattern. Let's look at this very right-hand side of this figure. For these two neighboring residues, T and E, you see this pattern. Okay, you see these two strips over here? They will share. They will have 2 peaks sharing the same frequencies. Okay? This is the type of pattern you're seeing. Because like I said, 2 of these peaks will come from the adjacent, will be coming from the adjacent residue. Now, when you start seeing this pattern, you can imagine a type of procedure of sequencing these strips. Essentially, you take these 2 strips, and you see whether they are sharing 2 peaks. If they are sharing 2 peaks, you place them adjacent to each other. And then you just continue this procedure, and you sequence these strips. Once you sequence these strips, all the atoms will get the frequencies, will get assigned with the frequencies. So this is the procedure that people typically do.
That's a sequencing procedure, not a structure determination.
Yeah, but once you sequence it, each atoms will get assigned the frequencies. Then when you get assigned, once it gets assigned a frequency, you can go to the next phase, which is you place the constraints according to the frequencies, and then you can do your
Nosy or whatever.
yeah. Then you do your structural determination by solving the distance geometry problem. And for a long time, well, for a while, I was solving the distance geometry problem. But then at some point, all the NMR spectroscopy told me this is the procedure to look at because it takes, for an experienced graduate student, it takes a day or two. For an inexperienced graduate student, it takes a week, or yeah, to do it. Okay. Right. Now, so it seems like a very simple procedure because you imagine you take this group set of 4 peaks, you just try to find the one that find the adjacent set of 4 peaks that matches, and then you just continue this sequencing procedure. However, the peaks are noisy. That means you probably cannot find something that matches exactly, and the peaks could be missing, and this will create an even more severe trouble because you couldn't even find anything that is adjacent to it. Or there could be artifacts, and peak list gets crowded when you have a lot of atoms in the protein, and it's really hard to segment out this tube of 4 peaks. Now, to tackle this challenge, we assume a generative model for the data, and we formulate the assignment problem as a maximum likelihood problem, and we solve it using an optimization procedure. That's the goal. All right. Before I move on, I just want to say something. So I'm going to call this a set of 4 peaks a spin system from now on. Okay? This is called spin system. This is something I will keep referring to. Okay? All right. So what have others done? So Professor Wojtowicz has actually worked in this field before. So here's a approach that they take. First, they construct some connectivity graph between the resonance peaks, and they use a clustering algorithm to construct this tube of 4 peaks. Once they form this spin system, the tube of 4 peaks, you start building small chains of a spin system, essentially using the procedure that I was mentioning. You fix one spin system, you just look through the other n-1 spin system to see whether there's a match. And then you just construct small reliable chain. Once you construct this small reliable chain, you try to assemble these small chains into a big chain using integer linear programming. Okay, so this is an approach that they have taken. And so FLYA is a very successful algorithm that chemists developed, actually by the giant AdBax group. So they first create a list of expected peaks based on the amino acid sequence that they know, and they map the experimental peaks to expected peaks via some genetic algorithm. That's what they have been doing. Okay. And so we're trying to be smart to formulate it as a QAP, but it's actually quite hard to beat the chemists, I must say. Okay, let me first discuss the generative model. We have each residue has if we strip off all the immaterial atoms, each residue will have a nitrogen, hydrogen, and a carbon alpha and carbon beta. So you have four peaks over here. Then, like I said, the spin system will also involve the carbons from the adjacent residue. So you have the carbon alpha and carbon beta from the previous residue. So this is the spin system. Okay. Now, as you can see, Si and S-1, Si-1, they will share two peaks. Then we perform a shuffling of the spin system. That means that we don't know how they are arranged into a sequence. And our goal is to find this pi shuffling matrix. It's a permutation matrix. Okay. All right, let's assume we have a protein of n residues. That means we have n spin systems, and we want to find this shuffling matrix pi. Okay, so like I said, we have some prior information on what kind of frequencies that a residue should take on. all right? We have some rough range. So that means given a residue Rj, okay, with some distributed according to some mean mu j and covariance matrix sigma j, this is the negative log likelihood of Si being the correct spin system for that residue, okay? Essentially, with the correct shuffling matrix or with the correct permutation pi, this should be small. The negative log likelihood should be small. This will give you a cost on constraining what this permutation matrix pi should be. Essentially, it's trying to encourage S pi I to lie in certain range of frequencies expected by the residue. The other cost is the following. We form this adjacency matrix Aij. Is coming from some metric between every spin system Si and Sj. This is essentially to saying if we are forming this is essentially saying if we have the correct shuffling matrix to adjacent spin system, S pi I and S pi I plus 1, they should have small discrepancy, okay? This is the second cost. Now, we write down the total cost. This describes the negative log likelihood of our data. And what we want to do is we want to find the correct ordering such that this is small. And as you can see, this is a quadratic assignment problem. Now, OK. Well, I should say the good news is this is just a particular instance of the QAP. But the bad news is QAP is actually hard to solve. If we write it in terms of the QAP form, this B is actually the path graph because we only have cost for two adjacent spin system. Okay, so Bij is a very sparse graph. It's actually a path graph. So in some sense, this is like a longest path problem in QAP. Okay, so in a matrix form, this is how it looks like. And the approach that we're going to take subsequently is to define a big variable Q. So by rewriting the first term in the Kronecker product form, we have this vec p transpose showing up. And we're going to redefine this vec p transpose as a large matrix Q. This is the type of approach that Professor Wukovich was taking in the 90s. And the next thing we're going to do, or Professor Wukovich had done, was to lift it. Okay, so now we have this big variable Q of size n squared by n squared, and P is a permutation matrix. And in 1999, Zhao and Professor Wukovich, they wrote a paper that they lift this matrix Q into a PSD matrix of size n squared by n squared, and P is relaxed to the set of doubly stochastic matrix instead of a permutation matrix. This is a very tight convex relaxation. You have a bunch of linear constraints coming from the fact that Q is originally coming from the permutation matrix. This is a very tight convex relaxation. However, it's only feasible for problems of, I mean, we can only solve it up to size n equals to 50, even with some homemade solver. But however, typical protein has like, I mean, at least 100 to 200 residues. Well, our observation is the following. We know that B is a path graph, so B is very sparse. That means that if we rewrite the QAP cost, the first term is essentially a weighted sum weighted by this Bij. So that means it only involves a few Qij blocks because Bij is sparse. Then what we're going to do next is we're going to drop all the irrelevant variables. We're not going to keep all the variables Qij. We're just going to keep all the Qijs involved in the optimization procedure. All right. So here's B, and here's an example. If we have a path graph, this is how the cost looks like. So it will only have the blocks on this diagonal. It will only involve these blocks on the diagonal. So if we drop all the Qij, that is, they are not along the diagonal, we're left with n minus 1, 2n by 2n PSD variables. This immediately helps us to reduce the problem size from n to the power 4 to n cubed. Well, we call this the E-SDP relaxation. It's a short for H-SDP. Now, instead of having a Q, that is the PSD Q, that is of size n squared by n squared, now, as you can see, we only have some order n by order n PSD matrix over here. Okay. Well, we have considered defining blocks of a size 2 by 2. We can also consider defining larger blocks, and we call this a Clique-SDP if we have a larger block to tighten the convex relaxation. All right. So relative to the method proposed by Professor Wojtowicz in the 90s, we lost all the linear constraints of the unseen blocks Qij, and we lost the positive semi-definiteness of Q. Okay. On the other hand, we only need to keep n minus 1 variables of size On by On. And the operations in the optimization scales like On cubed instead of On6. So the useful operations are essentially projection to the PSD cone. And now, since we are dealing with size n by n, the operations takes On cubed time. And the dual problem can be parallelized. So you have n minus 1 projection you need to do, and you can parallelize them. And in the following, in the numerical experiments, we actually distribute over 20 cores. Furthermore, if B is a chordal graph, we actually retain positive semi-definiteness of Q. Okay, so this is something we gain for free if B is a chordal graph. So for a size n equals to 150 graph, we actually are able to solve this problem within an hour. Okay, and we can also get so this is a convex relaxation which gives us a lower bound for the quadratic assignment problem, and we can also get an upper bound by just project the doubly stochastic matrix P into a permutation matrix to get an upper bound. Okay, that's a characteristic of this method that we're proposing. Now I'm gonna show some results. Well, I'm selecting sparse examples from the QAP library, and we're essentially competing with the eigenspace method proposed in 2016. All these are convex relaxation that involves size On by On matrix. We're not comparing with the original big SDP relaxation because it is just simply too big to run for these examples. And for this type of sparse graph, and we're getting very competitive lower bounds compared to existing On by On convex relaxation. So this SDMRS is the Peng and Mittelman convex relaxation.
Excuse me, what's the story with the negative columns?
This is the cost that's coming out from the relaxation.
It's really crafty.
Yes. Yes.
Why is there a star, no convergence to require precision?
So
whereas QPB does converge to require precision?
I forgot what precision that my co-author sets it to. It's something at 10 to the minus 4, 10 to the minus 5. Yeah.
What's the number of the residues in these cases?
This is for QAP library problem, which are so this is a graph size 12, 15, all the way to 25.
So the number here is our number of residues?
No, this is a very generic problem because our algorithm can work with a sparse graph in general, and we select out some sparse graph in the QAP library, and we perform our algorithm on it, and then this is the lower bound that we are reporting. I'm going to show I'm going to show results on for the case of protein structure determination. Okay. We run it all the way for a graph with size 128, and so for a graph with size 128, we are pretty much the only method that can actually run. Well, all the previous convex relaxation methods with size ON by ON doesn't readily give rise to a simple projection method to obtain upper bound, and therefore we can only compare with a non-convex optimization solver. It's a path for the QAP problem. Like I said, we get our doubly stochastic matrix, we project it to a permutation matrix, and we obtain an upper bound. And comparing with the non-convex optimization solver, so essentially they just relax the permutation matrix into a doubly stochastic matrix in the QAP problem and solve the QAP problem as a quadratic problem over the set of doubly stochastic matrix. And this is and we're getting better upper bound than they do. And well, I'm just going to repeat myself. And this is the type of complexity that we are getting compared to the eigenspace method. And as you can see, the complexity is about order 2. Is a factor of 2 better than the eigenspace method. Right. Now let's turn to the NMR problem. We evaluate E-SDP on the benchmark data set with 5 proteins. Okay. Like I said, we're going to construct the spin system, and we're going to, for the frequencies of the adjacent carbons, we add some noise. This is to create mismatch between the adjacent spin system. All right, we consider 2 levels of noise. One is a low noise regime, and the high noise regime essentially correspond to how much variance we add in this noise model. So for this 5 protein, we are up till now the leading method is IPAS, the method developed in Waterloo. We're getting similar results, or sometimes better results for this benchmark data set for the low noise regime, and for the high noise regime, we are getting near perfect recovery as well of the permutation matrix. Okay.
What do the pair of numbers mean?
What the pair of numbers? So yeah. So on the left hand side we have precision. Essentially, it is the correct assignment divided by the. So all these 4 algorithms, they don't assign everything. If they feel some spin systems are too unreliable, they wouldn't even assign it. Okay. So that means not all the spin systems are actually assigned. So precision is essentially the true positive. It's like the correct assignment divided by the number of spin systems that are actually assigned. And the right-hand side is recall. Is essentially the correct assignment divided by the total spin system. Yeah, so that's what the 2 numbers means. And a lot of time, true positive is what the NMR practitioner care for, because they really want something that is correct. Okay. And we have also tested it with 4 experimental data sets. But on the experimental data sets, our algorithm actually didn't perform that well compared to IPAS. So these are the 4 experimental data sets. And as you can see, the number that are correctly assigned. So for example, the first one, IPAS assigned 71 of them, and our algorithm assigned 50 of them correctly. So it's actually a lot worse than what IPAS is doing. And the reason is the following. When you have experimental data sets, you actually have a lot of missing peaks. So this is not simulated data sets, right? Like where all the peaks are present. Once you have missing peaks, you start to have ambiguity in assignments. And when you have ambiguity in assignments, your convex relaxation quickly loses tightness. And this is why we are not doing as well. And IPASS is doing all right because it starts building reliable small fragments, and those reliable small fragments are unaffected by whatever optimization procedure you have later. So this is the, well, our conclusion is, well, our method is not really the best method at this point. So, okay, I guess I have 4 minutes. Okay, all right, let me try to finish this third part in 4 minutes. Okay. Well, actually, I won't try to finish it in 4 minutes. So, well, please let me know if you want to hear more later. I'll just take it offline.
Time for questions.
Yeah, I have a question.
Yeah.
Can I have the third part in 3 minutes now?
In 3 minutes. Okay. All right.
Well, can you tell us something about this linear program?
Okay. Yeah. All right. All right. I'll show you some figure. Okay. How about this? Okay. Right. So we have a protein with residue R1 to Rn. Okay. Now we have some. Let's say we have some candidate spin system that already select out. So you can use enumeration, exhaustive search. You just build however many spin system you want. Okay? You build M of them. So for each residue, all this M spin system could be a possibility, right? You can assign any of this. You can build maybe 10,000 of them, 100,000 of them, well, depending on how much processors you have. Now, you start adding weighted edges between adjacent set of spin system, okay? Between two adjacent set of spin system, you add some weighted edge. And you can also filter out some spin system that really seems unlikely for each residue. Okay, so this is the type of a graph you have. So you have weighted edges between the adjacent set of spin system. Then you solve a shortest path problem or longest path problem that start from the beginning and it traces it all the way to the end. So this path should give you the minimum negative log likelihood. So you start by forming some weighted edges between every adjacent set of spin system, and then you solve a shortest path problem that traces through this graph. And then the path that it picks out should correspond to the negative log likelihood of the assignment. So this is the procedure, and because you can select as many spin system you like, you just throw in all the likely or unlikely possible combination of the spin system, and then you just run it. And all I want to say is, I'll show you the final results in the end, is that we're comparing ourselves with the algorithm that chemists developed, and we're actually getting competitive results, even comparing with chemists' algorithm. That's the message of the third part.
No, may I suggest the model, please? Linear model.
Yeah.
Okay. Graph.
Yeah, it's the vanilla shortest path problem.
Does it make sense to solve it with a formulation rather than combinatorially?
Oh, you mean with linear programming? Or
Yes, why linear programming instead of a shortest path,
you mean like dynamic programming?
for example?
Well, because we actually want to put an extra constraint over here that says that one spin system can only be used once. Okay, so essentially, we want to place this extra constraint. So it's not exactly shortest path, but with one additional, if you remove this one additional constraint, it is shortest path. It is, yeah.
Okay, let's thank the speaker.